Welcome to the 11th lecture for Physics 4C. We continue our introduction to special relativity with the derivation of a couple famous results from the postulates of the special relativity that we introduced in the last lecture set. Time dilation is the first example we will cover, demonstrating the result that moving clocks are slow. We then use this result in the Michelson apparatus setup to derive the length contraction, also known as Lorentz contraction, with the result that moving rollers are short. The formulas derived are then used in the classic example explanation of how cosmic ray muons travel a longer distance in the Earth's atmosphere than their short lifetime in their own rest frame would allow. We also look at a couple additional things that will help us as we get our bearings in special relativity. One is a convention around use of the word observing or observation as a special vocabulary that indicates that all the trivial corrections have been made. This use is borrowed from how David J. Griffiths uses them in his textbooks. The second is a look at the Lorentz factor gamma and the speed beta to start to develop a number sense with these common parameters. Next week, we will cover Lorentz transformation, which allows us to tackle all situations in special relativity in a systematic way.
Welcome back. So time dilation is the first consequence of this postulate of special relativity that I want to explore. So this is the thought experiment. Imagine you built a clock that operates this way. So you have a clock that operates by bouncing light back and forth between two mirrors. And so I have one mirror here, I have another mirror here, and if these two mirrors are separated by distance L, then when I have a light beam or pulse here, bounces up, bounces from here, comes down, then I can use that round trip as my ticking of a clock. Or I guess, let me use the round trip. So as it goes up, comes down, when it comes down here, then some amount of time has passed. That amount of time t should be equal to 2L divided by c. Good? I feel like this is particularly nice clock because we've been just told the speed of light is constant at c. So if I can keep this length stable, then c is guaranteed to be the same, then it'll keep the same time no matter what happens. Now, we want to explore what happens as this clock is moving. And we want to be careful in the specification here. I want to specify that this clock is moving in a direction that's perpendicular to this axis. So it's moving in a direction that's perpendicular. So it's let's imagine that the clock. Imagine that this clock is moving with the speed v in a direction perpendicular to the direction that the clock is oriented in. Yeah? So if you are an observer A staying with the clock, then nothing will change. That's the principle of relativity, right? So whether this reference frame is moving or is stationary, none of them makes a difference. From the person who's staying with the clock, nothing about the clock has changed. So I want to give it a special name. Let me call that proper time. So this time, let me call that, use a special letter, Greek, lowercase tau, to indicate this time. This is what we are going to call proper time. There's one special proper time for every object. Like my own proper time is proper time of the time kept by whatever reference frame I was in. Or like proper time of a train that's moving is the time kept in the reference frame where the train was stationary. So whoever's moving in the train. So let me call this proper time. Then what we want to look at is how does this clock look from the perspective of observer B. So from the perspective of observer B, who's sitting out here watching the clock move, does it still take the same amount of time for this light to bounce from one mirror to the other mirror and then come back? So from the perspective of B, are these two mirrors staying stationary? No, they are moving, right? So as this light reaches here, this mirror actually moves over here, right? And in the amount of time for the light to come back, this bottom mirror has moved even more to over here. Okay? So the path of the light for observer B should look something like this. So this is the path of the light that the observer B sees. Okay? And that's what he observes. And let's see how much time, at what time t, the light comes back to this mirror. Now, for observer A, who stayed with the clock, so if I'm drawing everything, so observer A was here when the light hit there, and observer A is here when the light comes back. This same amount of time would have passed for observer A. So we are looking at, for observer B, how much time passed? Well, I think I have all the diagram. I think I can figure out how much distance all this is. And how fast is light moving for observer B?
C.
Yeah, C, because that's the second postulate of special relativity. So I can calculate how much time this is. Let's do that and see how much that actually is. So I guess I need to first figure out the distance that the light has to travel in the reference frame of B. So this is an assertion that I'll need to make without spending too much effort trying to prove it. I think this distance is going to remain the same. It's the distance that's perpendicular to the direction of motion, and that in that direction, the length is not going to change. Good? Okay, as long as you believe that, we'll move on. So this height will remain at length L. And I can come back and double check this when we have introduced Lorentz transformation. It's easier for me that way. So I need to know the length of this side. Let me call that delta x. Then this is a right triangle. I can figure out the hypotenuse. The hypotenuse should be square root of L squared plus delta x squared. So I need an expression for delta x. How far did the mirror travel in half the amount of time for the round trip? Can I use this expression? Not quite, right? Because this is not the time for this. This is the time for this. So I have to actually leave this as an algebraic expression that this delta x is equal to speed times and some expression of this unknown time. So half this total amount of time. So t over 2. Yeah? And then return trip is exactly the same. So let me write down this algebraic expression and see if I can solve it for t. Okay? So the algebraic expression is the time of travel is equal to the distance. That would be twice this distance, square root of L squared plus delta x squared, which is the v squared t squared over 4. distance traveled divided by speed. What's the speed? C. Speed of light is always c. By the way, that's one easy answer you can always get when we do special relativity. No matter what the situation tells you, speed of light is always c. That's one of your postulates. Even when it doesn't make sense, you know it's at least correct. Speed of light in vacuum is always c. I mean, you know, I do want you to make sense of it, but that's at least it's like a mantra. All right, so I have that. So time of travel would be t. So all of this is equal to t. And if this is beginning to look familiar, it's because it is. It's like what we did before. I have t on both sides of this expression, so I'm not done yet. I have to solve it for t. So let me solve it for t. Square both sides. So I have 4 over c squared times this, L squared plus v squared t squared over 4 is equal to t squared. Collect like terms. Let me go step by step. Distribute this. So you have 4L squared over c squared. 4L squared over c squared plus 4's cancel. So I have v squared over c squared times t squared is equal to t squared. Now I can collect the like terms on the same side. So moving this over here, I get minus v squared over c squared t squared. That's equal to this. Factor out t squared, I get 1 minus v squared over c squared times t squared. All right, I'm going to solve for t in one single step. Everyone okay with that? Okay, let me do that. T is equal to square root of this. So 2L divided by c divided by this. Divided by square root of 1 minus v squared over c squared. Seems correct to everyone? Yes? Yeah. And let me introduce a new notation. So as we are going through special relativity, you are going to see this factor a lot. This factor of 1 over square root of 1 minus v squared over c squared. It just occurs so many times that if I had to write it down every single time I saw it, my hand will get tired. So there's, we call it gamma factor or Lorentz factor. We introduce this symbol, gamma, Greek letter, is equal to 1 over square root of 1 minus v squared over c squared. So standard notation for special relativity. It saves a lot of writing. So in terms of that, this t is equal to 2L over c times gamma. Or let's see, I see 2L over c was this proper type. So this is what we can say. This amount of time it takes for the light to come back, t is equal to gamma times the proper time tau. And this is the statement of time dilation. Does anyone see why we call it time dilation? Like everyone here knows what dilation means, right? Making things longer. Why are we calling this time dilation?
Because gamma is always greater than 1.
Yeah, gamma is always greater than 1. That's actually a good thing to note. Thank you, Gauger. Because, you know, gamma is this. This number, so V, we are going to, is this the right time to address it? So V is never going to be greater than C. You can see here that you run into some serious issues if V was ever greater than C, right? I think it's easier to say why that would be the case after we talked about relativistic energy and momentum. So we'll save that for next week. But V is always going to be smaller than C, which means 1 minus some positive number, square root. So this will always be smaller than 1, which means gamma will be always bigger than 1. So that's a good fact to know. Gamma is always greater than 1. And since you are multiplying the time kept by the clock itself in its own reference frame, multiplied by gamma, number greater than 1, this t is always going to be greater than the proper time. So we call, here's the thing. With the easy questions in special relativity, the most common mistake people make is forgetting which side something should be on. Like, is it tau equals gamma t, or is it t equals gamma tau? So to avoid the confusion, this is a helpful phrase to know. Moving clocks are slow. That's the English phrasing of time dilation. And this is the mathematical expression of moving clocks being slow. And this is what I mean by moving clocks are slow. So you see how fast this clock is going, 1 second, and imagine comparing against your own watch. If this clock is moving past you at some speed comparable to the speed of light, in the time it takes for this clock to count down 1 second, your own watch will count to something greater than 1 second. So this is slow. Yeah. So that's time dilation. So not that complicated. Yeah. But it is a bit unintuitive. And I guess what we'll skip in the interest of time, you can read about it in your textbook. So 5.3. Your textbook does give you some examples of time dilation. And the most, best known is measurement of the lifetime of muon. Muon is an unstable particle discovered in the 1920s, 30s, early 20th century. And the interesting thing about this is, so it has a very short lifetime. And if you are assuming non-relativistic mechanics, then that's not enough time for it to ever reach Earth from upper atmosphere where it's produced. But because of time dilation, enough of them reach us to actually measure things. So you can read about that in the textbook. So that's time dilation. It's maybe not what you would have guessed, but once you drive it following these steps, it makes sense, right? Once you believe this, then you can believe that this bouncing back and forth of light somehow takes longer as this clock is moving past you. Okay? Then the second effect that I think we do have enough time for is something called the length contraction, or sometimes we call it Lorentz contraction, after the guy who originally derived that expression. And I guess this is probably the good setup to use. In this, let me erase a bunch of stuff that was not correct. So once again, there's no such thing as an ether wind. So let me erase that. So no ether wind. And speed of light doesn't change as it's traveling. So, let me just make up some space here. And we'll use this setup for, so I want to actually use this Michelson-Morley apparatus to derive the second expression about length contraction. So here's the thing. Let's see. So this is what I want to be able to enforce. This is trying to make our theories so that it agrees with the experimental result that no shift of interference fringe was seen. There's no apparent difference in time of round trip this way and round trip this way when this entire apparatus, let me erase these two. When this entire apparatus is moving this way with the speed v. Good. Yeah. Just for reference, from what I got confused with earlier. Once you say apparatus is moving that way, the ether wind is going the other way. Good. Okay. So let's say, and what you will find is, if we simply say that so this portion of the arm acts like this clock that we just derived. So if while it's at rest, if it took this round trip time of tau is equal to 2d over c, then as this is moving, the round trip time of this will take more time by this factor gamma. So instead of this tau, as it's moving at speed v, the amount of time it takes will be gamma times tau. Now this is what I want to enforce. I want to enforce that the round trip time of along this arm to take the same amount of time as this. So that when they come back, recombine here, then there shouldn't be any interference fringe because they all come back at the same time. Okay? So let's try to figure that out. So I'm going to stay in my own, I guess, so let me set up my observers this way. A is the observer who's traveling with my Michelson interferometer. B is the observer who stays here and just looks at things passing by. And from the perspective of B, let me erase this because this was the ether in the stuff. From the perspective of B, this is how things appear. Let me draw the things on the top, which is just a copy of this. So from the perspective of B, as the light travels up, the entire apparatus moves over. So this moves over here. This moves over here. Light hits here. And by the time light comes back, this whole thing moves over here. And light comes back here. And after the light, let me draw this V up here. So by the time light gets to this here, and it bounces back this way. Good? All right. Let's see. All right, that seems okay, right? That's what B would see here. Now, let me be careful here. So I'm not going to try to do any comparison at these 2 points. So for A, these 2 events, call it C and D, they happen at the same time. But I have a nagging suspicion that for B, it probably won't happen at the same time because it's 2 events separated by some distance, like with the train example. So I'm going to wait until those 2 lights come back to the same point to compare them. So when they're happening at the same point in space and time, then I'm reasonably sure that it'll happen simultaneously. It's like, when this ball is dropping and like same ball dropping at the same point, well, it's going to happen at the same time with itself, no matter in what reference frame you're looking at it. So let me do the calculation. So I know the round trip time for this. Round trip time for the upper arm is T is equal to gamma times, call it 2D over C. That's what we did with the time dilation. That's kind of why we had to do the time dilation first. And let's try to figure out how much time this round trip should take. And we will say that whatever round trip time this takes must be equal to this. Okay? So let's see. I guess I need to figure out some geometry. So in the time that the light reaches here, let me call that T1. So this happens at time T1. The mirror moves by some distance. And that distance should be v times t1. Seems reasonable? Okay. And so that's not it. I mean, that's not the total time. There's the return time. So in the time that, let me call the amount of time or the time stamp at which light reaches here, let me call that T2. So this T2 is from 0 all the way to this moment in time. This apparatus has moved this distance. This distance here. So that must be speed v times T2. Good? All right, I think that's all the geometry I need to figure this out. Right? So, all right, the total travel time, let me call it, I guess I can call it T. It should be the same as this. So let me, total travel time T is equal to the time, I guess that should just be T2. So, T2. And let me rewrite it this way. It's T1 plus T2 minus T1. Okay? And I can figure out T1 based on geometry. So at time T1, this has happened. The apparatus moved forward by this distance, or the mirror moved forward by the distance, and the light, which is our measuring stick for a lot of things, light has traveled the distance of d plus this. So let me say, so light has traveled d plus vt1. That's the distance that the light travels. So that's the distance. So that's equal to speed of light, c, times t1. Distance light traveled, distance light traveled. Okay? And I just want to warn you, in case I run out of time, we are going to get a little bit of contradiction. And when we run into that, we'll have to make a little correction. Okay? So, all right, so let's keep going. So I can solve this for T1. In fact, let's do that now. I'm not making any, okay. So if I solve for T1, T1 is equal to, move this over, so C minus V divided out. So T1 should be D divided by C minus V. Everyone good? Okay. And I can figure out T2 minus T1 as well. So the light is starting from this point. So it's traveling this and the distance of the this d plus vt1 minus this. So the distance that the light is traveling, that is this distance here. That's so this whole thing, d plus vt1 minus this bit here, v times t2. Good? And that should be equal to speed of light times t2. Notice how I'm using the same speed of light for both portions of round trip. It's, what is it because of? Yeah, second postulate of special relativity. So, if anything else is confusing, at least this, you can get speed of light is constant at c. Like, once again, I hope everyone eventually has an understanding of what that really means, but at least you know the correct answer, and you can understand it later, if necessary. Okay, so let me, wait, C times, not T2, it's a T2 minus T1 is the actual amount of time that the light spends. Good? All right. Oh, actually, let me rewrite this way. I think this will make my algebra a little bit easier. D minus V times T2 minus T1. Good, that's the left-hand side. So that means I can move this over. So I have actually C plus V. And when I divide it out, this is what I get for T2 minus T1. T2 minus T1 is equal to d divided by c plus v. Good? Okay, let's plug these in, these two expressions into up here and see what we get. I'm just going to move back here and write those expressions down. So total time t is equal to that d divided by c minus v plus this, plus d divided by c plus v. Let me combine the fractions. So when you combine the fractions, you get, so product of these two, c squared minus v squared, like you saw before. Okay, let me factor out d times, so c plus v plus c minus v. V's cancel out like before. I have 2c, so you end up with, this is equal to 2d times c over c squared minus v squared. Let me do a little bit of factoring that similar to what I did before. I'm going to factor out a factor of c on the denominator that doesn't really exist. So it's like, so let me do it in two steps. Multiply top and bottom of this fraction by 1 over c. That makes the numerator 1 and the denominator c minus v squared over c, right? And I'm going to factor out this c from the denominator. Then I get this c here. So this turns into 1. This doesn't really have a factor of c, but I can still factor out a c by turning this into square. Okay? So this becomes 1. So with all those corrections, this is what it is. 2d over c times 1 over 1 minus v squared over c squared. That looks familiar, right? That's gamma squared. So let me just do that. So this is equal to gamma squared. And this is where you run into a little bit of contradiction. This is the expression we are trying to get to. That total time of travel is gamma times 2d over c. I have total time of travel is 2d over c. All right, so far so good. But I have gamma squared. What did I do wrong? So let me save a little bit of time. Math-wise, I didn't do anything wrong. My algebra was fine. So what it is this d turns out to change. For us to be able to enforce this experimental requirement that these two light beams arrive here at the same time, turns out the only way to make that true is by allowing this length to change. It's such an unintuitive thing. It's like somebody telling you that this ruler is 30 centimeters long, but when it's zooming by you, it's going to be shorter than 30 centimeters. If it's moving at, I don't know the actual remember numbers. Let's say it's moving at 3/4 of speed of light, then instead of 30 centimeters, it's 15 centimeters or something like that. But that's the only way to make this consistent. Make this consistent with this and still not abandon the second postulate of special relativity. So you know what Sherlock Holmes said, once you eliminate the impossible, whatever remains, however improbable must be true, that's that thing. So what no law of physics tells you is that this length must be the same in all inertial reference frames. That's what our intuition says it is, but I told you from the beginning, your intuition is wrong. And there's no law of physics that says that the length does not change when you are in different inertial reference frames. So that's what I'm going to do. So let me make this correction. Wherever I had d before, it's going to become d prime, new length. And I'm going to I'll make that new length whatever it needs to be so that this expression will be equal to 2d over c times gamma. That's what it must be equal to. So let me, so this is the d I'm going to keep as d. So let me track down all the other d's. That's d prime, 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 prime. I guess that's all I have to do. I mean, I can prime all these, but it's implied. All right. So let's figure out what this d prime is. I can cancel out 2c, 2c. I can cancel out one factor of gamma. So I get d prime. So that's the length of this arm from the perspective of B. D prime is equal to D. So let me give it this D a name. The same way I gave the name for the time kept by the clock in its own reference frame, I can call this D proper length. It's the length of whatever object it is in its own reference frame. So the proper length of this ruler is 30 centimeters, no matter what reference frame you are in, because when I say proper length, I mean the length measured in its own reference frame. Okay, so that's the proper length. So d prime is equal to this proper length divided by gamma. Okay? So that must be true because I have laws of physics constraining what I can do. I have experiment telling me that these two light beams must arrive at the same time. And I have a second postulate of special relativity that tells me speed of light cannot change on return trip. The only thing I can change is this. So that's going to change. Okay? So this is what we call length contraction or Lorentz contraction. So this is length contraction. And let me just end with length contraction. For the sake of symmetry, let me end with the same phrase or similar phrase as what we had for time dilation. For length contraction, we say moving rulers are short. Moving rulers are short. Good?
It says, oh, I guess before I didn't do this question because I thought this would be nice for a tutorial, which it is. But since I have time, let me just work this out. It's actually a really nice setup. I think your textbook even uses this as an example. It's a classic example. Let me see that your textbook does. I think it would use it as an example for time dilation. That's the classic example. Yeah, half-life of a muon. It's an entire subsection. And I think see, want to see if yeah. This picture, this kind of summarizes the calculation that we are going to go through. So the place it comes in the textbook, they're talking about this before they introduce the length contraction. Now, in Earth's reference frame, if a muon has to travel this distance, then the amount of time that the muon lives for is longer than how long it lives in its own reference frame because of time dilation effect. Then you might try to look at how does it look from the muon's perspective, because its proper lifetime will be just proper lifetime. How does the muon get to the bottom of the mountain? And the answer is length contraction. From the muon's reference frame, Earth appears length contracted. So the distance that muon has to travel, or more precisely from muon's perspective, the distance that the Earth has to come closer is actually shorter due to contraction. So that's what the question is getting at. Let's just work through it. It says, suppose a cosmic ray colliding with the nucleus in Earth's atmosphere. Oh, do I want to Yeah, it's let me just show you the image so that cosmic ray shower. So that when it describes this production of muon in the upper atmosphere, you have some picture to associate with. There are some really nice artists' drawings of these. I think this is the one that I like. So, or one of the ones I like. This okay, this is enough. So, what this is illustrating is the cosmic rays, which are highly energetic protons from outer space, um, colliding with just the gas molecules in the upper atmosphere. You can almost think of it like a proton-proton collision. There's a lot of energy there. It produces a bunch of unstable particles. The first particle they usually produce are pions. That's what these are showing. And these pions will, some of them, they decay into muons. So this is a picture of a positively charged pion that's decaying into muon. So the muon is created here. And the question is basically getting at, okay, how far does it travel before it decays? So, so that's the picture. Not that you need it. You don't really need a picture, but we'll get to particle physics towards the end of the semester, and there's a lot of fun stuff we can talk about. So, cosmic ray produces a muon that has this velocity. So, or in the parameter that I've been using, we would say, okay, beta of that muon is 0.98. And for later, when I need it, gamma will be 1 over square root of 1 minus beta squared. And I have a feeling I'll probably need a number a few times. So let me just work it out numerically and just have it available. 1 over square root of 1 minus 0.98 squared. Okay. 5.025. I'm just keeping one extra significant figure just in case. 5.025. Okay, how long does the muon live in Earth's frame of reference? That's time dilation. So the formula that you need for time dilation is that in the lab frame where the muon is moving, it's going to be living for its own proper lifetime multiplied by gamma. So this will be, well, let me just write down gamma tau for now. And I'll plug in all the numbers in all together. How far does the muon travel according to the earthbound observer? Oh, so sometimes we ask a pretty mundane question, you know. This is something you've known since physics 4a. Distance traveled is speed times time. And this is, it's just kinematic, so it's as valid as it was before. The only thing that's a little bit more exotic in this context of special relativity is that this time, instead of being the proper lifetime tau, it'll be gamma tau. It'll be the time dilated lifetime. So the muon travels, I'll just have to watch out for these units later when I plug in the numbers. It'll be moving at its speed, beta c, times the duration of time, which is gamma tau. Plug in the numbers, that's the answer. Okay. How far does the muon travel relative to Earth according to the muon's perspective? Oh, yeah. Sorry, that's a very convoluted way of asking. So if you imagine you are the muon, then you are not the one that's moving. It's the Earth that's moving towards you. And as the Earth is moving towards you, well, you could describe it as how far you move relative to the Earth. So for that scenario, so the situation of a muon and Earth, it's symmetric. If a muon is moving at 0.9 AC when Earth is at rest, then when the muon is at rest, Earth is moving at 0.9 AC. So same speed as in the muon's reference frame, Earth is moving at the same speed that muon is in Earth reference frame. Now what changes is the duration of time. In this expression for speed times duration of time, the speed hasn't changed. That's still beta c. but the duration of time is going to be back down to tau, not gamma tau. And part D gets to that example that I was pointing to earlier. So, given that muon has 5 times as, in muon's perspective, there's 5 times as less time. How does the end result end up being the same with the perspective in B and C? It's that, well, it's because distance between Earth's surface and upper atmosphere is shorter, length contraction, by this factor gamma O. I didn't realize question did that for me. So that's why it's because that distance is length contracted in the shorter amount of time in muon's reference frame, it still travels between the two same points. So let me plug in the numbers here. I guess I can just type in the numbers. So gamma tau in microseconds, that'll be 5. Is this gamma times 2.2 microseconds. It's a proper lifetime. So 11.06, or I think if I say 11, it'll say it's correct. Yeah. And sorry, I just realized I positioned these well. Should have positioned them to the right. Okay. Okay, 11 microseconds in Earth's frame of reference. And in this 11 microseconds, 11 microseconds, it travels 11 microseconds times beta 0.98 times c, approximately 3 times 10 to the power of 8 meters per second. Do I want to? Let me do it this way. I'm going to do the unit conversions in place here. So here, this is the muon's lab lifetime, but it's in microseconds. So I need to multiply this by 1e minus 6 to convert from microseconds to seconds. All this will give me an answer in meters. I want that in kilometers. So I'm going to multiply it by 10 to the power of minus 3 so that the meter answer gets converted to kilometer answer. So, okay, 3.25 kilometers. That seems reasonable. It's a little bit on the shorter side, but I think it is actually right. Muon produces way up in the upper atmosphere, have a not as good a chance of reaching the ground. Okay, how far does the muon travel relative to Earth according to muon's perspective? Oh, yeah. So that's comparing these two expressions. They're different by gamma, so I can take this last answer divided by gamma, which is 5. Oh wait, I wrote it down. Gamma. So 0.647 kilometers. That should be it. Let's see. Good. Yeah. So that's and I think this is basically a numerical version of this example in the textbook. Relatively simple question, no paradoxes here. At least once you figure out which effect is what you should pay attention to in two different reference frames, then I think it's all good.
Well, let me give you a quick preview of what we are getting to on Thursday. And I want to explain a little bit of language that I'm going to be using while we are in special relativity. It's a shorthand to avoid having to do a lot of tedious clarification over and over. It's the use of one special vocabulary, observation. So I mean, in everyday English, the word see and observe means the same thing. You observe what you see. But I'm going to reserve this word observation in special relativity to mean something that's entirely different from seeing. So let me put it this way. How many of you here have some sense of how far away stars are? really far away, right? Do you know what the closest star that's not our sun is? How far away it is? No, it's not that far. In terms of light years, it's actually pretty close. Light years are a very reasonable unit of measurement for astronomical things. Alpha Centauri, how far away is it? No one has them memorized? No one here is an astronomy major? I think 3.4, some like 3 or 4 light years away. So let me introduce a diagram that I'm going to be leaning on a lot, especially as we introduce the tools we are going to introduce on Thursday. And let me try to explain this distinction between seeing and observing in the way I'm using the word, in special relativity. I'm actually borrowing this from a popular upper division textbook author, Griffith. He wrote a textbook for, I guess, arts majors called Revolutions in 20th Century Physics that actually explains conceptual ideas even better than a lot of more rigorous textbooks do. And so this is the distinction between observing and seeing. And once again, I'm just trying to clarify the new strange definition I'm going to be using. It's a shorthand so that I don't have to keep reminding you that we have to make this correction every single time. So I'm going to, let me describe this distinction using something called the space-time diagram. So in space-time diagram, what you do is you illustrate motion in one-dimensional. So if you're drawing this in 2 dimensions, motion has to be one-dimensional motion, and passage of time in its own axis. So you do plot something with an axis like this. The position along the horizontal axis, trying to remember the conventions. Time along the vertical axis. Yep. So let me ask you this somewhat inane question. So imagine this, it's night, so you can see the night sky, and Alpha Centauri. I don't know what constellation that's in. Let me, so it's winter, so you can, when it's at night, you can see the winter triangle. There's Sirius, which is one of the brighter stars. Let's just say Sirius is, I don't know, 10 light years away. I don't know the exact number. So let me ask you this question. Can you, let's see. 2 separate questions. One, is it possible to see light emitted from Sirius right now? Why not?
Because the light needs time to travel.
Light needs time to travel. A different question is, can you observe light emitted by Sirius right now? And I'll tell you the answer is yes, with a very convoluted definition of the phrase observe. So let me illustrate it on this diagram here. So on the space-time diagram, this is how you might illustrate sort of Earth, Sirius, and light from Sirius, all that stuff. So let's say this is where Earth is. And I can actually plot the trajectory of the Earth on this space-time diagram. I'm going to use Earth's frame, which means Earth starts at position x equals 0, and it remains at position x equals 0 for all time, meaning it'll just stay here. It's kind of boring. Good? Yes? And for the sake of this discussion, let's say Sirius is at relative, like stationary, like relative velocity between Earth and Sirius is 0, which I'm pretty sure is not true, but let's just say it is. So Sirius is out here at 10 light years away. Yeah? And the trajectory of Sirius would look like this. And these are all the different moments in time for Sirius. So when I talk about light emitted by Sirius, it would be, well, this light here. Light being emitted at this moment right now, simultaneous with when I say the word phrase right now. And it takes time for this light to travel. It'll take this light 10 years to get to us. So it'll take this light 10 years to get to us. So this is our 10-year mark. The light will finally reach us and we'll be able to see it. So now, 10 years from now, when we finally see that light, will our astronomers think that that light from Sirius, that's what's going on with the Sirius star right now? No, our astronomers are not stupid. They are smart. They know how to correct for the travel time of light. And this is the sense in which I'm always going to use the word observe. When I say the word observe, we have already corrected for this travel time of light. Because I want to assume that our observers, A and B, I want to assume that they are smart. They know how to make these trivial adjustments, right? Like all of you are smart, you know how to make that adjustment. And I'm making the same assumption for A and B. They know how to make those adjustments. So when our astronomers see the light from Sirius 10 years from now, they know that that's the light that was emitted right now, not 10 years later. So that's why I can say, so when I say observe the light right now, no, it does have to wait 10 years for me to actually make that observation, draw that reconstructed picture. So that's the sense in which we are going to use the word observe. And here's really the reason I'm going through all this painstaking detail to distinguishing between these two. I want to draw attention to how I phrased these two phrases. Moving clocks are slow, moving rulers are short. I didn't say moving clocks appear slow. No, moving clocks are actually slow. This is how we observe moving clocks. We have made all the trivial adjustments that can be made. After having done all of that, there's a real physical effect remaining, meaning moving clocks are slow. And the same thing with the rulers. Actually, with the moving clocks, it's kind of easy. If you work in particle physics, this kind of thing happens all the time in particle accelerators. Like particles with a really short lifetime live a lot longer as they are kept in the synchrotrons. So this is kind of trivial matter now. Moving rulers are harder. We don't have any spaceships that move at relativistic speeds. But I'm still claiming that moving rulers don't appear short. They are actually short. So we have corrected for any trivial effect from the travel time of light. After having done all that, these are the real effects that remain. So whenever I say the word observe, that's what I want you to understand, that we have already made those trivial adjustments. And whatever remains is the, property of the universe we live in, space-time we live in. It's the actual real property of the nature. It's not just some artifact of, it takes light time to travel. And one other thing I want to note is, even though we are going to be using light to illustrate a lot of these things, none of the special relativity is actually specific to light. It's the property of the space-time itself. So gravitational waves, which you recently heard got detected, also travels at speed of light because gravitational waves also move through space. When we get to, maybe when we get to quantum mechanics, essentially any particle with a zero mass will travel at speed of light. So sorry, that's a little bit too far ahead. So even though we are using light as an example, because it's a convenient example, what we are talking about is the property of the universe itself, not any particular one example.
Having good intuition for properties of gamma and beta is useful not in just writing down Lorentz transformation, but also in answering various questions that relate to relativity. There's really a reason we define these parameters. Let me start out with the beta, even though it's not the first thing we define, so that I can use beta for the other definitions. So beta is defined as the speed at which something is moving, v divided by c, speed of light. Both of these quantities are that people have experience measuring. And given this beta, you can write down the gamma factor, which is 1 over square root of 1 minus beta squared. I just have this memorized. And the question says they are useful in writing down Lorentz transformation, and they are. But what I want to show you is that it's not useful just for that. It's useful for other things, and I think the full application of this it's easier to see next week when we are going to be dealing with relativistic energy and relativistic momentum. Because what you're going to see is that relativistic total energy, it has this really simple expression that it's not something complicated like 1/2 mv squared or 1/2 mv squared plus mgh. All these terms that you have seen in classical mechanics, it turns out they are much more complicated. Maybe not much. They are more complicated than the relativistically correct expression for total energy, again, which we'll cover next week. That's given by gamma times the rest mass times c squared. That's it. That's our total energy. And the relativistic momentum will be gamma, same gamma there, and times m times a v velocity. So you can kind of see the hint of the non-relativistic approximation here. It's a little bit harder to see here. I'll leave that for next week. But for now, what I can say is that there's a really intimate relationship between energy and momentum, which are very important dynamical quantities, and gamma, and here it's written as mv, but I can write it out this way: gamma times m times beta times c, that's speed, and then whatever direction the particle is going. So when you look at gamma and beta, there's a quite intertwined relationship. So we'll get to that next week with the relativistic dynamics. I think for the remainder of today, want you to have some number sense for beta and gamma, which are described this way. But I think when you're trying to get a number sense for these quantities, it's useful to have these three different expressions, which I will numerically plot, so that we can start to gain that number sense. So one quantity is gamma, and I guess we can write it in terms of beta, 1 over square root of 1 minus beta squared. So that's what we had before. And we can solve for beta in this expression. I've done that before and got square root of 1 minus 1 over gamma squared. That's sometimes useful. Well, let me leave it here and show you some numerical plots to maybe try to gain some intuitive feel for this. There are some properties that's good to know, and you can kind of see them here. With this expression, it's not immediately obvious, but maybe you remember trivia like this. Speed of light is the universal speed limit. If you know that as something that someone who understands a little bit of modern physics should know, then great. What this means is that V is less than or maybe equal to C. And putting in this relationship here actually gives you this relationship that beta is less than or equal to 1. Because V could be C, in that case it'll be equal to 1, and otherwise it's less than 1. And if we're talking about the absolute value of beta, as in the speed, not velocity, then this is, of course, also greater than or equal to 0. So that's one thing that puts constraints around the beta Once you see that, then you see the constraints around the gamma as well. Imagine plugging this in. When you put in 0 for beta, then I have 1 minus 0, 1, square root of 1, 1. So we get 1 as the smallest value that gamma might take. This is when beta is equal to 0. And in terms of upper limit, I hope you see that as beta approaches 1, not when it's equal to 1, because then you're dividing by 0, but as beta approaches 1, you get this. 1 minus a number ever getting closer to 1, so it's a very small number. Square root of a very small number is still kind of small. 1 divided by that small number is large. So this gamma has no upper limit. So as beta approaches 1, gamma will approach infinity. And that's what you would see on a plot here. Let me see if I can plot this. So your textbook kind of has a version of this plot. Let's see. So let me declare my variable, beta. And I'm trying to plot gamma, which is 1 over square root of 1 minus beta from, I don't know if I remember the syntax. Beta going from, I think 0 is fine. I don't know if I want it to go to 1, 0.9 maybe. What does it plot? If it doesn't do something reasonable, I will look up the syntax and yeah, okay. So this is what it plots. And for this plot, I stopped it at beta equals 0.9, and it maxes out at 3 point whatever. But I'm not limited to that. I don't have to stop at 0.9. I can go to 0.99. Then gamma maxes out at around 10, but I don't have to stop at 0.99. I can go another 9. And I hope you are beginning to see the pattern here. So as beta approaches 1, this will be approaching a vertical asymptote. So beta will never, for massive particles, beta can never equal 1. And as beta ever gets closer, ever infinitesimally get closer and closer to 1, your gamma will increase without limit. So let me just do one more and one more. So at some point of a scale of gamma, it's like all these are so small compared to this that it's basically 0 or basically 1. And let me just put many more 9s here. At some point it'll complain, I think. But yeah, okay, I think I messed it up. I don't know how it's plotting, but I think I don't have enough samples for that. So, anyways, so yeah, that's how gamma depends on beta, and this relationship is a bit. At some point, it's a bit pathological in that it's not very well behaved. I mean, normally when you look at numbers like 0.49 and 0.59, we are used to thinking of those as two basically same numbers. They are basically 1. But when you are looking at the value of gamma, whether it's 4 nines or whether it's 5 nines, actually has a big difference. So it's I guess that's what I mean pathological. They are not well behaved. What you will see much better behaved is beta in terms of gamma. So let me plot beta as a function of gamma. So I'm going to, let me declare variable gamma again. And let me just plot square root of 1 minus 1 divided by gamma squared. Oh, wait, sorry. When I was plotting, sorry. when I was plotting gamma, this should have been squared. And what that'll do is that actually makes it even worse because, wait, does it make it worse? I think it makes it actually slightly better because this thing that I had before, if this is squared, then it's slightly better behaved because, well, not that much better behaved. Yeah. So note that missing square from previous results. But in terms of the qualitative behavior, that square doesn't actually matter that much. Let me plot beta as a function of gamma. So beta as a function of gamma goes as square root of 1 minus 1 over gamma squared. And gamma is, this is where I have to be careful. Gamma starts from 1. And let's say gamma equals 10. That's actually quite relativistic. That's where there's a factor of 10 time dilation or length contraction. This is the behavior you see. And I think in some sense, this might not look all that well behaved because as you plot bigger and bigger gamma, in comparison to that scale, this looks like a very sharp corner. So other than it's a sharp corner approaching horizontal asymptote, maybe where this beta as a function of gamma is useful is at very high gamma you can basically treat beta as equal to 1. That itself is, I think, useful because in that limit, so whether I'm comparing gamma going up to 50 or whether I'm looking at gamma going up to 100, the kind of the amount of precision I keep in gamma, it doesn't get worse. I actually, when I specify gamma with 2-3 significant figures, I actually know beta much better than 2 or 3 significant figures in terms of the number of nines. Where it's actually interesting is in the small gamma limit, as in where you have gamma that's close to 1. So maybe gamma plus 1 times 10 to the power of minus 2. Or maybe even smaller than that, 10 to the power of minus 5. So this would be like a non-relativistic regime. And that's where you see this kind of a nice-ish relationship between gamma and beta. It's so as gamma increases tiny bit over 1, your beta goes from 0. If this reminds you of kind of rotated around the parabola, that's because it is. Because the gamma factor will relate to kinetic energy. And as you might remember, kinetic energy goes as 1/2 mv or m beta c squared. So this is the kind of the low speed version that's showing that correspondence with the non-relativistic results that you are familiar with. So yeah, I think I just wanted to talk about these relativistic parameters, gamma and beta, and their numerical properties, because having this sense of intuition about their numerical properties will help you when you work through relativistic dynamics, and you will see some algebra tips later on that actually relate to these. Later on, as in next week. But in the meantime, I just want you to bring some attention to these two relativistic parameters that you will see a lot as you work with relativity, and it's worth developing some sense of intuition.